block. So, all right. So we have number 12. At what altitude above the Earth's surface is the gravitational field strength equal to g over 9? Now, little g here. Well, that's the variable we use for gravitational field strength. But there are some numbers that are so commonly used that we think of as shortcut form. All right, like the number pi. Right? What's the shortcut notation for pi? Well, what's the actual value of pi? And keep going for infinity, right? So what's the, rather than writing that out every time, what's the shortcut notation for pi? The Greek letter pi. The symbol, right? So some numbers that we use very often, we come up with shortcuts to write them because it's just easier. Little g, when it's just written like this, means the gravitational field strength at the surface of the Earth, which we actually have on our equation sheet. It's down here at 9.81 newtons per kilogram. So when you see just little g as taking the place of a number, it's just using that shortcut because we use that number a lot. It's not, and then we have the variable that's, we'll get to with the how part. So they're saying at what altitude above the Earth's surface is the gravitational field strength 1/9 of what it is on the surface. That's really what the problem is saying. So it's a gravitational problem. Do we need a diagram? No, not required. We got to do some of this y in words stuff, which is, this one where we have that rubric, the 40-40-20 rubric. We could put a diagram in there, and it might even be useful.
Why not?
Okay, so I'm going to put, there's the Earth, right? There's my point, where it's little g over 9. Little g. This is the altitude, right? And this would be the radius of the Earth. Yes? Now, what contributes to gravitational field strength? The distance from where, though? From the center. So, I think that's important to show. The distance to the center of Earth contributes to the grav field strength. Wow, I ran out of room there. Whoops. And I think it's key to realize that it's from the center of the Earth to that point, not from the surface. That would be a very common mistake. And you'll see mathematically how that comes in. What else? What else? Well, what creates the gravitational field? What about the Earth makes it have a gravitational field? It's mass. So I'm going to even just say that straightly. The mass of the Earth creates the field. Does there have to be something at that point to kind of interact with the Earth? No. That's the idea of the field. It's created by the mass. It's a way to describe kind of the influence the Earth has on the area around it. That's the difference between it and, say, a gravitational force on it. Let's see. Did I show I understood the physics? Well, yeah, I showed that I understand that it's created by the mass, and then I have to look at my distances from center, not from surface. clear links to the problem. Yeah, I got a nice diagram that links it, and I mentioned Earth both times, which is what the problem's about. Did I include any equations? No. Did I say I'm going to plug into this? No. So I didn't tell how to do it, I just explained why. Right? All right, let's move on to the how. So first thing I want to do is grab an equation from my equation sheet. I'm going to grab little g, planet equals big G, mass of the planet over how far you are from the center squared. That's here on my equation sheet in the far right corner of the forces and gravity box. And then from the back of my sheet, I'm going to grab that big G, the universal gravitational constant, is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. That's from the back of my equation sheet. Or I could memorize it. But I grabbed it from the back. And I should probably grab that little g is 9.81 newtons per kilogram, also from the back of my equation sheet. So all the black numbers are just copied from my equation sheet. Okay. Questions or anything before I dive into the deep end? All right, so let's just put in what we know. Oh, wait a minute. What planet are we talking about? Earth, right? So probably behoove us to have the mass of the Earth. That's on our equation sheet too. What a useful piece of equipment. So 5.98 times 10 to the 24th kilograms. So mass of the Earth. 5.98 times 10 to the 24th kilograms. All right. So let's see. In the problem, they told me that the gravitational field strength at this point is G over 9. So that would be G, which is 9.81 newtons per kilogram, over 9, equals, oops, I'm going to move all this down. Oops. There we go. Equals big G, 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. So I better make sure my mass is in kilograms and my length is in meters, right? Because that's I've established. Oh, and newtons and kilograms over here too. So, okay, so mass of planet. The planet is the Earth. And then how far am I from the center of the Earth? Well, I was thinking about our diagram back up here, right? Because how far it is from this point to the center is the altitude plus the radius of the Earth. Yes? So we're saying that this whole thing is R, how far I am from the center of the Earth. Do I know the altitude? No. Oh, good. I have a variable at least. It's always weird to do math when you don't have a variable. Or at least algebra. Do I know the radius of the Earth?
Yes.
How do I know the radius of the Earth? Wow.
So,
No. Definitely not that. Radius of the Earth, 6.38 times 10 to the 6 meters. Oh, good, it's even in meters, because that's what I wanted, right? There we go. So altitude, which is what I'm looking for, plus 6.38 times 10 to the 6 meters. Times 10 to the 6. How many meters is times 10 to the 6? Let's see, times 10 to the third is 1,000 million. So the radius of our Earth is about 6 million meters. And then, oh wait a minute, let me check my equation. Okay, I put in G, I put in big G, I put in the mass, I put in the radius. Oh, I almost forgot. Square that radius. And then you're just solving for altitude, right? So it's just algebra now. You guys can do algebra, right? What's your if you can't do the algebra that's involved here, how do you solve it? What's your helper for math? Well, if you don't look at our links page, there's some helpers down the bottom for math. I like to use Wolfram Alpha myself, but it's just alpha. All right, so we're looking at number 6. And number 6, we've got these can of soup and a jar of pickles, and they're separated by a small distance, less than half a meter. And they're asking, what's the force of gravity that they exert on each other? Oh, we know right away that those two forces make up a force pair, right? So this is number 6. So the two forces are a force pair. So equal in magnitude, oops, that's an N, but opposite in direction. Are they, because they're gravity, are they attractive or repulsive? They're attractive. Attractive since grav interaction. Let's see. What else determines anything about the gravitational force between these two things? Anything else contribute to the gravitational force between the can and the jar? The distance between them. How does that? What happens if I increase the distance?
The gravity is less.
Is less. So I'd write it like that. If increase distance between, now this is where I want to make it about this problem, can and jar, then grav decrease. Anything else contribute to the gravitational attraction or interaction between the can and the jar? I heard it. The mass. What would happen if I increased the mass of either one? Yep. Let's write it that way. If increase mass of either grav increases. Good. I'm just going to move forward because, well, time's running out. From my equation sheet, I'm going to grab this big equation, which is known as Newtonian's gravitational equation. All right? And then I'll also grab, this is a number that I use so often I stored it in my calculator. So I don't even have to type it in anymore, which is kind of nice. Yeah. So those are from my equation sheet. Now I can just plug in, right? Making sure that I have everything in meters and kilograms. So I'm looking for the gravitational force. I have big G. Notice I plug in with units, right? Then the mass of 1, let me call my soup can 1. It's 0.15 kilograms. Mass of number 2, 0.38 kilograms. And then the separation between their centers, I'm going to assume that separated distance is between their centers because they're trying to make my life nice. 0.42 meters, quantity squared. Most common math mistake will be forget that squared in there. Now I've got meters squared, cancel meters squared, kilograms squared, kilograms squared. I'm going to end up with an answer nicely in newtons, which is what they want. I think it was the F block. I drew a picture of the can and the pickles, which is a really good picture. So you find yourself a time to kill.